Hello my friends and welcome back to the You Can Do TV channel. Inside the manufacturing complex of AirPro Fan and Blower Company in Wisconsin, industrial fans and blowers are engineered and built to deliver reliable airflow solutions. The process begins with application engineering, where specialists analyze performance requirements and develop precise 3D designs. Raw materials are prepared and cut at the East Plant, while the West Plant focuses on machining shafts, hubs, and fan wheels, followed by dynamic balancing. Final fabrication, coating, assembly, and full-speed testing take place at the North Plant, ensuring each unit meets strict performance, vibration, and quality standards before shipment to industries around the globe. Precision engineering defines modern aluminum extrusion tooling. At Thumb Tool and Engineering, specialists develop fully customized dies tailored to unique aluminum profiles and press specifications. Tooling systems may weigh up to 50,000 pounds and reach dimensions of 6 feet in diameter. Production integrates advanced CNC machining, high-temperature heat treatment approaching 860 degrees Fahrenheit, and rigorous dimensional verification. Each design is optimized for alloy behavior, extrusion velocity, and finishing requirements such as anodized or coated surfaces. Through refined metallurgical control and consistent die geometry, the tooling delivers highly stable extrusion performance and exceptional first-run operational reliability in exacting industrial applications. At the Desio manufacturing facility of Flowserve, pump production for large desalination systems follows a highly controlled industrial process. Structural components, produced to ensure corrosion resistance in seawater environments. After casting, precision CNC machining forms critical geometries such as hydraulic passages, shaft bores, and sealing surfaces. Careful material preparation and expertise in high alloy metals ensure durability under high pressure and saline conditions. Rotating components are dynamically balanced to a G1.0 standard to minimize vibration and improve operational stability. The machined parts are then assembled into complete pump units, including bearings, shafts, and sealing systems. Each finished pump undergoes comprehensive performance verification, including full-speed hydraulic testing with power capacities reaching 18 megawatts. These validation procedures confirm efficiency levels exceeding 90% and ensure reliable operation in large-scale reverse osmosis desalination plants. Since 1965, Aeros Hydraulic has specialized in the engineering and manufacturing of advanced hydraulic cylinders and power units for industrial and mobile applications. Large cylinder manufacturing represents a core technical capability. Piston rods with diameters up to 450 millimeters can be machined with turning lengths reaching 12 meters and individual weights up to 6.5 tons. Raw materials are stored in automated high-bay warehouses and cut to size before entering CNC-controlled turning and milling operations. Manual deburring and dimensional inspection ensure high surface quality and precise tolerances before further processing. Certified welding procedures and specialized fixtures support the assembly of complex hydraulic systems, including cylinders, control units, and power aggregates. Each hydraulic cylinder undergoes rigorous testing at pressures between 1.5 and 2 times the intended operating pressure, verifying structural integrity and performance reliability. Surface finishing is completed in an environmentally responsible paint facility using layered airless coating technology. Annual production includes tens of thousands of hydraulic cylinders designed for heavy-duty sectors such as machinery manufacturing, industrial automation, and energy systems. These components deliver durability, operational stability, and compliance with international safety and quality standards. High-precision machining is critical for producing large, forged valve bodies used in high-pressure energy systems. At RE Machining, heavy steel forgings, such as 13-inch class 15,000 valve bodies, are processed using advanced equipment, including the Trevisan DS1200. The machining sequence includes multi-axis milling, deep boring, precision drilling, and threading operations designed to meet extremely tight dimensional tolerances. Rigid fixturing and high-torque spindle capacity allows stable cutting of dense forged material. Careful control of tool paths and surface finishing ensures accurate sealing surfaces and internal flow passages, delivering components capable of withstanding extreme pressure and demanding industrial service conditions. At Bruck, complex industrial components are delivered as fully assembled turnkey systems. The facility includes a large assembly and testing pit, measuring 8 meters wide and deep and 11 meters long, built on solid rock with no structural weight limits. Components up to 16 meters high and 50 tons are assembled using heavy-duty cranes. Processes include precision bolting, welding, and shrink fitting with induction heating or dry ice. Static pressure testing reaches 600 bars, while dynamic simulations replicate offshore operating conditions. High-performance machining of large cast iron rings requires powerful equipment and heat-resistant tooling. On a Heller Combined Processing Center, a raw casting weighing about 2,000 kilograms undergoes several precision operations. The process begins with rough turning using ceramic inserts capable of handling high cutting temperatures. Finished turning follows to achieve accurate dimensions and surface quality. Subsequent milling with a D80 cutter, equipped with ceramic inserts, shapes key surfaces. Large diameter drilling using a D90 solid drill with carbide inserts creates internal passages, while a D109 counterboring operation finalizes critical mounting interfaces. At the Desio facility of Flowserve in Desio, advanced pump manufacturing integrates engineering, casting, machining, and testing into a unified production process. Engineering teams design pumps and develop customized hydraulic solutions based on specific industrial requirements. High-integrity metal castings form the structural foundation of each unit, before precision machining produces critical components such as impellers, casings, and shafts. Assembly operations integrate mechanical elements with strict dimensional control and rigorous safety procedures. Comprehensive quality assurance governs every stage of production. Final performance validation takes place in specialized test facilities, where pumps undergo hydraulic and operational testing to verify efficiency, reliability, and compliance with stringent industrial standards. Industrial roll manufacturing is a highly specialized sector within heavy industry, combining advanced metallurgy, large-scale engineering capabilities, and precision mechanical expertise. The products created in this field play a critical role in metal forming and rolling operations, particularly in steel and other heavy manufacturing industries, where durability and performance are essential. Companies operating in this area typically work with extremely large components that require robust production environments and specialized equipment capable of handling very high weights. The materials used must be carefully designed to provide a balance between strength, toughness, and resistance to wear, ensuring that the rolls can withstand intense mechanical pressure and continuous industrial use. A strong focus is placed on material quality, structural reliability, and consistent mechanical properties. This often involves the use of advanced alloy technologies, strict quality control systems, and highly skilled technical personnel. Modern facilities are equipped with heavy-duty machinery and precision manufacturing systems that allow producers to achieve the high standards demanded by industrial customers. Beyond the technical aspects, successful roll manufacturers rely on coordinated logistics, experienced engineering teams, and long-term collaboration with clients in the steel and processing sectors. By combining technical expertise with industrial-scale capabilities, manufacturers are able to deliver reliable solutions that support demanding production environments around the world. In heavy industry, bearings are the critical components that keep rotating machinery operating reliably. At SKF, bearing remanufacturing services are designed to restore worn components and extend their operational life, while reducing downtime and maintenance costs. The process begins when used bearings arrive at specialized remanufacturing centers such as those in Hanover, Pennsylvania and Birmingham, Alabama. Experienced analysts first conduct detailed inspections to identify damage such as wear, surface etching, or particle denting caused by harsh operating conditions. Based on this evaluation, engineers determine the most effective restoration procedure. Critical bearing surfaces are then repaired through precision grinding and finishing processes performed on the same machines used in new bearing production. If necessary, damaged components are replaced to restore proper geometry and load distribution. Throughout the process, high-precision measuring equipment, accurate to within a few microns, verifies dimensional tolerances and surface quality. After restoration, bearings are tested and documented to ensure performance comparable to new components. This remanufacturing approach not only extends service life, but also reduces life cycle costs and energy consumption, providing a sustainable and cost-effective solution for maintaining industrial rotating equipment. Few musical instruments combine metallurgy, precision forming, and acoustic craftsmanship as closely as a professional cymbal. At Avedis Zildjian Company, the production of each cymbal follows a carefully controlled sequence of thermal treatment, mechanical shaping, and acoustic tuning developed over centuries. Manufacturing begins in a restricted melting room, where a proprietary bronze alloy, often referred to as the Zildjian secret, is transformed into cast metal blanks. After cooling, each casting is weighed, sorted, and transferred to high-temperature furnaces operating at approximately 1,400 degrees Fahrenheit. Heating prepares the alloy for mechanical deformation during the rolling stage. Once removed from the furnace, the hot bronze blank is passed through heavy rolling mills that gradually flatten the material into thin discs. This cycle of reheating and rolling is repeated 5 to 6 times, refining the internal grain structure while achieving the necessary thickness and flexibility for further forming. When the required dimensions are reached, hydraulic presses form the central bell of the cymbal and punch the mounting hole. The disc is then trimmed into an exact circular shape corresponding to the intended model diameter. Excess metal from trimming is recycled back into the melting process. Acoustic character begins to emerge during hammering. Rotary and impact hammering systems apply controlled patterns across the cymbal surface, redistributing internal stresses and shaping tonal characteristics such as sustain, pitch complexity, and projection. The cymbal is then placed in specialized die presses that apply up to 80 to 90 tons of pressure to establish the final curvature and taper profile. Lathing follows as the cymbal rotates on a precision lathe, while cutting tools remove thin layers of oxidized metal. This operation fine-tunes the weight range and reveals the distinctive spiral finish associated with many cymbal models. Sharp edges are carefully smoothed before surface finishing. Some models receive a high-polish, brilliant finish, while others are coated with a thin protective layer that prevents oxidation without altering acoustic response. Each cymbal is finally stamped, laser engraved with identification markings and serial numbers, and evaluated individually by experienced sound testers. Only cymbals that meet strict tonal and cosmetic standards are approved for packaging and worldwide distribution to professional musicians. At the casting base of Lianghu Valve Group, valve body production relies on advanced precision casting and metallurgical control. The process begins with detailed engineering design and mold preparation, tailored for large diameter and high-pressure valve components. Molten alloy steel is melted under controlled conditions and poured into precision molds to form dense structural castings. After solidification, cast parts undergo cleaning, shot blasting, and grinding to remove scale and surface imperfections. Heat treatment cycles are then applied to improve mechanical strength, refine the grain structure, and enhance resistance to pressure and corrosion. Dimensional finishing and machining ensure accurate sealing surfaces and connection interfaces required for industrial valves. Each casting is subjected to strict inspection procedures, including dimensional verification and structural quality testing. This integrated manufacturing system ensures durable valve bodies capable of reliable performance in power generation, petrochemical processing, and other heavy industrial applications. Industrial hydraulic cylinders, operating in mining and heavy machinery environments, require periodic refurbishment to maintain performance and structural reliability. At Montan Hydraulic, the repair process restores worn hydraulic components through a sequence of specialized mechanical and surface treatment procedures. Maintenance begins with complete disassembly of the hydraulic cylinder. Internal sealing systems and guide elements are removed and replaced with new precision components, to restore pressure integrity and alignment of the piston assembly. Articulated bearings at the cylinder joints are also exchanged to ensure smooth load transmission during operation. The piston rod undergoes advanced surface restoration, including chrome nickel coating that improves wear resistance, corrosion protection, and sealing surface durability. Additional protective engineering solutions, such as specially designed stone impact shields, are developed to protect exposed components in harsh operating environments. Structural components are cleaned through abrasive sandblasting, removing corrosion, old coatings, and contaminants from the cylinder housing. Following surface preparation, a renewed corrosion protection coating is applied to extend service life in demanding outdoor conditions. Hydraulic valve blocks integrated with the cylinder system are inspected and repaired where necessary to guarantee accurate flow regulation and pressure control. Precision reassembly ensures correct alignment of internal components and sealing systems. Before returning to service, the refurbished cylinder undergoes rigorous hydraulic pressure testing. The pressure test verifies structural integrity, sealing performance, and operational safety under working loads. Through this comprehensive refurbishment process, large hydraulic cylinders regain full operational capability and extended service life in heavy-duty industrial and mining applications. Cast iron manhole covers play a critical role in protecting underground infrastructure and maintaining urban safety. In cities around the world, these covers shield water, sewer, telecommunications, and gas networks, while preventing flooding, traffic hazards, and environmental damage. Production begins with detailed engineering drawings created using computer-aided design systems. These designs define dimensions, locking mechanisms, and structural features required for high-load urban environments. The manufacturing process then moves to metal melting, where ductile cast iron is heated to approximately 550 degrees Celsius in electric induction furnaces. This controlled melting ensures uniform chemical composition and mechanical strength. Molten iron is poured into precision molds formed through an EPC casting process. During solidification, the metal forms dense structural components capable of withstanding heavy traffic loads and harsh environmental conditions. Once removed from the molds, the castings undergo shot blasting to clean the surface and remove any remaining sand or impurities. Machining operations follow, including lathe finishing that ensures precise fit between the cover and frame. Accurate tolerances are essential for maintaining stable seating and preventing unwanted movement or noise during service. Surface protection is achieved through an epoxy powder coating process. The coating is applied and cured to create a durable barrier against corrosion, moisture, and chemical exposure. Each product then undergoes automated inspection and testing to verify structural integrity and dimensional accuracy. Through this integrated production system, Segye Cast Iron manufactures advanced safety locking and floating-type manhole covers designed for reliability, ease of operation, and long-term performance in demanding urban infrastructure systems. At Train Parts Sweden AB, leaf springs are manufactured and refurbished to ensure reliable suspension performance for rail vehicles and heavy-duty transport systems. The process begins with high-strength spring steel plates that are precisely cut and shaped according to specific load and flexibility requirements. The plates are then heat-treated to achieve the necessary hardness, elasticity, and fatigue resistance. After forming, each leaf is assembled into a spring pack with center bolts and clamps that maintain alignment under heavy loads. Surface finishing and protective coatings are applied to prevent corrosion and extend service life. Finally, the completed leaf springs undergo strict dimensional checks and load testing to verify durability and performance in demanding railway operating conditions. The Trevisan DS600 Machining Center, developed by Trevisan Machine Utensili SPA, combines advanced turning and milling technologies in a single high-performance platform designed for complex metalworking operations. At the heart of the turning system is a plan slide unit with a 600 mm diameter rotating head and a CNC-controlled U-axis with a travel of 200 mm. This configuration allows a single cutting tool to perform contour turning on both small and large diameters. The system is capable of producing spherical and conical surfaces, as well as carrying out boring, back-facing, and threading operations using standard turning tools. Constant cutting speed control ensures optimal tool life and consistent machining productivity. For milling operations, a high-speed spindle located beneath the plan slide enables drilling, tapping, thread milling, and other axial machining processes. The spindle can automatically receive an angular milling head from the tool magazine, expanding the machine's versatility. During milling operations, the turning slide remains locked in position to maintain structural stability. The machine structure features a welded steel bed with stress-relieved construction, providing high rigidity and efficient coolant and chip evacuation. The spindle head is manufactured from mehanite cast iron to enhance vibration damping and durability. All machine axes are equipped with heavy-duty linear guideways and high-performance servo drives, operating through large pitch ball screws for precise movement. The DS600 also incorporates a dual pallet system with 900 x 900 mm pallets mounted on a continuously rotating table with a high-precision angular encoder. A 54-position tool magazine with a double gripper manipulator and the patented TG2000 tool holder system ensure rapid tool changes, high rigidity, and efficient metal removal during demanding machining operations. The VDF 450 Horizontal Turn Mill Center, developed by VDF Boehringer, is engineered for complete crankshaft machining and high-precision production of complex shaft components. Designed within the VDF series platform, the machine combines turning and milling capabilities to deliver high productivity, low part costs, and reliable operation in both high-volume and flexible batch manufacturing environments. Its robust structure is built around a polymer concrete machine bed that provides exceptional rigidity and vibration damping, ensuring stable machining even during demanding operations. High-quality linear roller guides and advanced drive systems maintain precise axis movement and long-term dimensional accuracy. This design supports simultaneous machining processes, enabling efficient production of automotive crankshafts, shafts, and chuck parts. Additional auxiliary functions and tooling capacities allow multiple operations to be performed in a single setup, significantly reducing handling time and increasing manufacturing efficiency. With its durable construction and modern control technology, the VDF 450 offers a reliable solution for consistent, high-precision machining in advanced industrial production systems. Complex aerospace components require exceptional precision, advanced machining strategies, and absolute reliability. By consolidating the entire process into one continuous program, manufacturing efficiency and dimensional accuracy are significantly improved. The machining process is performed on the YCM Alliance RX65 5-axis CNC machining center, a compact but highly capable platform designed to handle complex, multi-axis operations. Despite its relatively small footprint, the machine can accommodate large components while maintaining the rigidity required for aggressive metal removal and precision finishing. This capability makes it well suited for aerospace components with intricate geometries and tight tolerances. Production begins with rough machining, where a high-performance end mill from Kennametal removes large volumes of material at high speed. Rapid roughing establishes the overall geometry of the piston housing while preserving enough structural rigidity for the subsequent precision operations. After the initial roughing stage, the machining program proceeds with facing and boring operations that refine the main internal bore, one of the most critical functional features of the part. To achieve the required dimensional accuracy, a precision boring bar equipped with adjustable inserts is used to bring the bore to its final specification. Tight tolerance control is essential because this internal surface directly influences the component's performance and sealing characteristics in the propulsion system. Additional operations continue within the same machining cycle. Small channels and detailed features are milled using miniature cutting tools from OSG. Threaded holes are produced through roll tapping, a method that forms threads by displacing material rather than cutting it, creating stronger threads with improved surface quality. Larger threaded features are produced through thread milling, which provides precise control of thread geometry. Once drilling and threading operations are complete, ball end mills finish the exterior surfaces of the housing, producing the complex curved contours required by the design. Additional slotting operations create tool access, so finishing cutters can reach difficult internal areas. The final contouring stage is performed, while the component remains attached by small tabs, ensuring stability during machining. After separation from the stock material, the finished part is placed in a tumbler for polishing, producing a clean and uniform surface finish. By eliminating multiple setups and integrating every operation into a single machining sequence, this manufacturing approach dramatically improves repeatability, reduces alignment errors, and demonstrates the power of modern multi-axis CNC machining in aerospace production. Slewing ring bearings are manufactured through a sequence of forging, machining, and inspection processes designed to ensure strength and precision. Production begins in the forging workshop, where steel billets sourced from major steel mills are cut and prepared. The billets are heated in natural gas furnaces and shaped using a 1,600-ton press and a CNC ring rolling machine to form large forged rings. After forming, the rings undergo heat treatment processes such as annealing, normalizing, quenching, and tempering to improve hardness and structural stability. The forged rings are then transferred to the machining workshop for precision processing. Using advanced CNC machine tools, operations such as rough turning, finish turning, drilling, and raceway cutting are performed. Raceway grinding ensures smooth rotation and high load capacity, with machining accuracy reaching approximately 0.03 millimeters. CNC machining centers equipped with automatic tool changers allow drilling and milling to be completed efficiently under computer numerical control. Gear manufacturing is also carried out in the same workshop. Gear hobbing machines cut both internal and external gear teeth for slewing bearings, meeting precision standards of level 7 to 9. Quality inspection is performed throughout production, including chemical analysis, hardness testing, ultrasonic testing, and metallographic examination to ensure reliability in heavy machinery applications. The Pestan spiral pipe corrugated polyethylene pipe produced by Pestan is designed for large-scale sewer and drainage infrastructure. Manufactured using spiral winding technology, the pipe combines a corrugated external structure with a smooth inner surface to provide high structural strength and efficient flow performance. Diameters range from 300 mm to 3,000 mm, while pipe lengths are available from 1 to 6 meters to suit different installation requirements. Ring stiffness classes from SN4 to SN32 allow the pipes to withstand heavy loads in urban street sewer systems. During installation, pipe sections are aligned on the construction site and joined using electrofusion welding technology. In this process, specialized electrofusion couplers containing embedded heating elements are placed around the pipe ends. When electrical current is applied, the polyethylene surfaces melt and fuse together, forming a strong and leak-proof connection. This installation method ensures excellent sealing performance, high corrosion resistance, and long service life, making spiral pipe systems suitable for demanding municipal sewer infrastructure projects. A massive stainless steel process column is transported to the blast and paint yard for surface preparation. The column measures 100-inch internal diameter and 218 feet long, weighing about 440,000 pounds. Fabricated from 2-inch thick 304L stainless steel, it demonstrates heavy-duty industrial fabrication and logistics. Pima CM55 Pima welding automation is engineered for precision preparation of circular weld seams. Using automated milling instead of extensive thermal cutting reduces welding volume, lowers defect rates, and saves production time. Hydraulic leveling, automatic depth control, and an integrated monitoring system ensure fast setup and accurate seam preparation. At the intelligent manufacturing base of Sany Renewable Energy in Beijing, advanced digital technology transforms the production of modern wind power equipment. The facility represents one of the first fully connected 5-gram smart manufacturing plants in the wind energy industry, designed to deliver higher quality, improved efficiency, and safer production environments. A flexible manufacturing system enables the simultaneous assembly of multiple wind turbine models ranging from 2 MW to 8 MW capacity. Automated logistics play a key role in the production flow. Heavy-duty automated guided vehicles transport large components through integrated warehouse systems, allowing continuous material movement across the assembly line. Key production stages incorporate unmanned operation concepts. Automated yaw assembly units distribute heavy components with high precision. While intelligent robotic systems perform complex operations such as blade grinding using laser-guided composite robots. Automated painting and stud installation further increase consistency and workplace safety. The factory also operates through a digital twin platform that integrates production data from the entire facility. This smart manufacturing architecture supports real-time monitoring, data analysis, and optimized coordination between design, production, and management processes in large-scale wind turbine manufacturing. At New England Electropolishing, stainless steel components are refined through a precise electropolishing process that enhances cleanliness, corrosion resistance, and surface smoothness. Parts first undergo detailed inspection and specialized pre-cleaning, including descaling and pickling to remove oxides and contaminants. They are then processed on dedicated electropolishing lines designed for 300 and 400 series stainless steels. Controlled electrochemical finishing smooths microscopic surface peaks, producing a bright, ultra-clean finish. Final visual inspection and careful packaging ensure consistent quality, particularly for demanding medical and precision manufacturing applications. The welded field moment frame system, developed by Side Plate Systems, improves both structural performance and construction efficiency in modern steel buildings. Installation begins with verification of anchor bolts and column elevations. Moment frame columns, typically fabricated as two-story sections, arrive on site with side plates and deck support angles already attached. Using lifting lugs or chokers, cranes position the columns onto the foundation before temporary construction aids maintain the required spacing between the side plates. Moment frame beams are then lifted into place between the plates. The beams include top and bottom cover plates and vertical angles designed to ensure proper alignment during installation. After the structural frame is aligned and tightened, field welding completes the connection. Horizontal fillet welds join the side plates to the beam cover plates, while vertical fillet welds connect the side plates to the beam angles. Once welding is finished, decking and fire-resistant materials can be applied, creating a durable and highly reliable steel frame connection system. The FEMA Giotto Evo cutting system developed by Technica is engineered for precision and efficiency in advanced material processing. The machine integrates a circulating band knife system with an oscillating band knife mechanism, creating a double cutting system capable of delivering clean, accurate cuts across complex shapes and varying material thicknesses. An integrated sharpening system maintains blade performance during operation, ensuring consistent cutting quality and extended tool life. The equipment also features a motorized conveyor table that enables smooth and continuous material handling throughout the cutting process. To enhance automation and accuracy, the machine includes a size detection system that measures product dimensions in real time. A central support structure stabilizes the workpiece, while the automatic rotating table positions materials for optimal cutting orientation. Together, these technologies allow the Giotto Evo to achieve precise, high-productivity cutting in modern manufacturing environments. At the intersection of heavy industry and advanced engineering stands Domi Machina, a manufacturer specializing in machinery for the production of welded steel pipes used in water, oil, and natural gas transmission systems. The core technology centers on spiral welded steel pipe manufacturing. In this process, steel strip coils are first flattened and guided through forming rollers that gradually shape the material into a spiral configuration. The edges of the strip are then precisely angled according to the required pipe diameter before entering the submerged arc welding stage. Here, the seam is welded both internally and externally to ensure structural integrity. Each weld is inspected using automated ultrasonic testing systems that verify the quality of the joint along the entire pipe length. Once the pipe body is formed, automated plasma cutting systems trim the pipe to the specified length. Conveyors and rolling equipment transport the pipes through cleaning and finishing stations before further processing. Additional equipment opens welding vents at pipe ends to facilitate field installation and correct edge distortions caused during cutting. Quality assurance is critical in pipeline manufacturing. Hydrostatic testing machines inject pressurized water into each pipe to confirm leak resistance, while real-time radiographic inspection systems detect hidden weld defects. The production line can also integrate coating technologies capable of applying epoxy, polyurethane, or polypropylene layers for corrosion protection. Beyond spiral pipe systems, Domi Machina manufactures ERW pipe profile machines used for industrial pipes and structural profiles. Through continuous investment in research, engineering, and automated production systems, the company delivers complete turnkey solutions for modern pipe manufacturing facilities worldwide. Leaf springs are critical suspension components used in heavy vehicles, rail systems, and industrial equipment designed to absorb shocks and support large loads. The manufacturing process begins with high-strength spring steel bars or plates that are cut to the required lengths according to the design specifications. The steel pieces are then heated in furnaces to high temperatures to make them suitable for forming. During the forming stage, hydraulic presses and specialized rollers shape the heated steel into curved profiles that provide the spring with its required elasticity and load-bearing characteristics. Each leaf is carefully formed to maintain uniform curvature and structural consistency. After shaping, the springs undergo heat treatment processes, such as quenching and tempering. These treatments significantly improve the mechanical properties of the steel, increasing its strength, fatigue resistance, and elasticity. Following heat treatment, machining and finishing operations are performed. Holes are drilled for center bolts, and clamps or bushings are installed to assemble multiple leaves into a complete spring pack. Protective coatings are then applied to prevent corrosion and extend service life. Finally, each leaf spring assembly undergoes load testing and dimensional inspection to ensure it meets strict quality and safety standards. before being delivered for use in demanding transportation and industrial applications. The UPI successfully completed a complex marine pipeline installation for the NCC Power Project at Krishnapatnam, delivering a 3.1-kilometer seawater intake and outfall pipeline system. The project involved installing a 1,600 mm outer diameter intake line and a 1,400 mm outfall pipeline designed to transport seawater for power plant cooling operations. Production and preparation began with pressure testing of large polyethylene pipes to verify structural integrity and leak resistance. Reinforced concrete anchor blocks were then installed along the route to stabilize the pipeline against underwater currents and buoyancy forces. After assembly, the long pipeline sections were carefully towed offshore to the installation location. Engineers installed flange joints and bend restrictors to maintain alignment and protect the pipeline from excessive stress during operation. The final stage involved controlled sinking of the 1,600 mm pipeline into its seabed position, completed successfully on April 26 to 27, 2013, ensuring reliable long-term marine infrastructure performance. The tire manufacturing process at Toyo Tires follows a carefully controlled industrial sequence to ensure durability and performance. Production starts with the mixing stage, where natural and synthetic rubber are blended with carbon black and chemical additives to create specialized compounds. The material then moves to extrusion, forming components such as tread and sidewalls. During calendering, rubber is pressed with steel or textile cords to create reinforced layers. After cutting the materials to precise sizes, the tire building process assembles all components into a green tire. The curing stage applies heat and pressure to vulcanize the rubber. Finally, finishing and inspection verify balance, appearance, and structural quality. Manufacturing a precision saw blade involves several controlled machining stages. Steel plates are first laser cut to shape, followed by quenching to increase hardness. Teeth milling forms the cutting geometry, while lathing finishes the outer diameter. Subsequent grinding sharpens the teeth, including TCT inserts. High frequency or flame hardening strengthens the edge before final inspection, finishing, and packaging. On modern construction sites, Nucor rebar fabrication introduces a new level of efficiency with the autonomous TY-Bot rebar tying robot. Moving smoothly along screed rails, the machine navigates its work area without mapping or calibration. Capable of performing more than 200 precise ties per hour, TY-Bot works day or night, rain or shine, delivering safer, faster, and more consistent reinforcement installation on large concrete structures.